everybody. Thank you very much, Piero, again, for giving us the opportunity to present our SEEC photography project, and thank you everybody for coming. So we are SEEC Photography, as Piero said, and we are doing photography at the speed of light. But how does that happen, or how can we do that? Well, we will explain it today. But first, let's start from something simple. If we think in the word photography, the beginning of the word photo is the Greek for light. And if you are able to see me right now, it's because there's light coming from the light sources up there, and the light reaches my body, then light is scattered from my body to your eyes, and then your eyes send the signal to your brain.
But of course, when we say that light comes from this bulb up there and it reaches my face and then it reaches your eye, then we kind of imply that light is moving. And you could ask whether that is true, and if it is true, you could ask how fast is it actually moving. And the first one, or one of the first ones who actually tried to test this was Isaac Beckmann in 1629. And the way that he did it was that he was standing on one mountain. I have to say he was Dutch, so I don't think the mountain was that high. He was standing on a mountain, and then a friend of his, in this case Philip, was standing at the distant mountain, and he was holding a mirror. And what he then did was that he said, well, if light is moving at a finite speed, then I should be able to measure the time it takes for the light to go to the mirror and come back again. So he would switch on his light source and see when the light comes back. Now, of course, in 1629, he didn't have a torch, but what he actually did was that he blew up a bunch of gunpowder, because that was the brightest light source that they had at the time. And we will just see, you know, this is really simple, and since it's so simple, we will just try it here. So I will see whether I can measure the time from me pushing this button to me seeing the light. Well, it's red light. Let's try it with the white light, if I can make it work. Yes, here. So the problem is I could not measure it, right? So when I'm doing this, all that I can say is that either it is moving really fast or it's instantaneous, meaning that I push the button and the whole room is filled with light. So if it's really fast, what you can do is you can, of course, increase the distance in between those two mountains here. But again, that was hard at this time because they already used the brightest light source that they had. So instead, what was done about 35 years later was that Ole Römer was looking at the sky. And he was sitting on Earth, and he watched the moon Io as it would go in circles around the planet Jupiter. And he would note the times at which the moon Io would hide in the shadow of the planet. So for example, let's let it revolve one more time. For example, now it's hiding in the shadow of the planet. And he noted this time, and he did this not only once, but many times. And so he realized that this would happen every 42 hours. So again, if this is on August 21st at 10 in the morning, then it would happen again on August 23rd at 4 in the morning. Let's see whether that's true. It is true. Good. So it works. It happens every 42 hours. So he could also say, well, if that's the case, then in about 3 months from now, it should happen on that particular day at that particular time. But what happens when you wait long, then you see that the Earth is moving around the sun, right? And also the planet here is moving, but it's not as fast. So about 3 months later, this distance is now much longer. So if light travels at a finite speed, it will take the light longer to go from the moon Io back to Earth. And this is exactly what he could measure. He could see that it took the light 20 minutes longer than it should, because it would hide in the shadow 20 minutes later than he thought. And from this he could come up with a speed of light, a finite speed of light that is already really close to the value that we know now, which is 299,792,458 meters per second. So this is really fast. That means if those two mountains were at the distance of 120 yards, it would have taken light only 0.0000037 seconds, and that's of course the reason why I couldn't see it. But of course you could also ask whether this is true, right? Maybe your vision is much better than mine, and you could actually see this very short time scale. So let's just test it. You can see a screen here, and on this screen you see a blinking square, and it starts to blink slowly, but it will blink faster and faster with time now, every quarter of a second, every fifth of a second. And you will see that at one point it's so fast that you can no longer tell whether the square is on or off, whether it's black or white. So now to my eye it already starts to flicker. Now I'm having a hard time to say whether it's black or white, and now I really cannot tell. To my eye it's more or less gray now, and even more so now. And this is now when the time to blink is on the order of 10 to 20 milliseconds. So this is really the fastest that we can see. This is also the reason why movies are taken at frame rates of 24, 25 frames per second. This is the reason why computer screen works at 100 Hertz, because there would be no point in making it even faster because our vision cannot follow that. So we now know that vision is not faster than 10, 20 milliseconds. We also know that light moves really fast. So this is an indication that there are many things in our world that we cannot see simply because our vision is too slow. So let's just take a minute to look at the kind of the time scales that govern our life. We are all very familiar with this time scale here. 1 second, that's about the time it takes for a heart to beat. 1 billion times longer than that, that's about my age, that's about 32 years. 1 million times longer than a second, that's about 12 days. And 1,000 times longer than a second, that's about 16 minutes. Now you all know, of course, what 16 minutes are and what 12 days are and what 32 years are. The reason why I'm putting it up there is because I want you to get a feel for what the effect of 1,000 means. What does it mean if something takes 1,000 times longer, right? And of course, there are many more things that can happen in 32 years than in 12 days. And now we will go to the other side. So we will go to slower and slower time scales and see what happens there. 1,000 times shorter than a second, that's a millisecond, and that's about the time it takes a housefly to beat its wings. 1,000 times shorter than that, that's already a really short time scale. Even a fastball, if you throw it as fast as you can, doesn't move by more than the width of a human hair during this short time. Okay, so it's already really short. 1,000 times shorter than that, that's now a nanosecond. And we've seen on one of the previous slides that within 1 nanosecond, light moves by about 1 foot, by about a distance like that. And 1,000 times shorter than that, that's a picosecond. And that's now really the time scale on which a chemical bond forms or breaks. So there are many things that are going on these time scales, on these short time scales, but we just cannot see them with our bare eye. That's why we need some help. And we will show you some movies later that are done on this time scale. So we will show you movies where 1 frame takes only about 40 picoseconds and where the whole movie takes only about 10 nanoseconds. And Philip will explain you how this is done.
So one of the first pictures taken at this very short time scales between here is shown here. It was taken in 1972 in the US in the Bell Labs, and it shows a laser pulse moving through a bottle filled of a scattering liquid. These guys at the time were able to have shutter times as small as 30 picoseconds. So in order to take such a picture, one needs 2 things. So first you need a short laser pulse. If you have like a long laser pulse, this is a laser which is always on, it would just be a line. As well, you need a very short shutter time in order to freeze this moving light pulse in time. So like if you want to make a picture of a fast moving car, you need a short shutter time on your mobile phone or analog camera. So analog cameras use normally like mechanical shutters. But mechanical shutters or mechanical parts, for them it's very hard to compete with the speed of light. So in our case, we use an electrical switch to realize that. So how do we do that actually? So we have a photon, which is the smallest unit of light, which is scattered from an object, afterwards collected by our camera lens. And in the camera, we transfer this photon to an electron. And now this electron we can gate or block with a very fast electronical field, switching a very fast electronical field. And the speed of an electrical field is the speed of light. So if this electron is gated, so this is the shutter, if this electron is gated, we amplify this electron to a lot of electrons, and then we convert this electron back by a fluorescence screen to a lot of photons, and these photons are then collected by a CCD chip. In our case, we don't do it just with one photons and one pixels, but with a lot of pixels next to each other in order to form a picture. So how is actually the process of us like taking a movie showing the speed of light? For that I would like to show you a small animation. So in the background you can see our lab in Stanford, and the laser pulse is released from a laser. Afterwards we focus it through a lens in order to expand it afterwards over the whole room. And now if we have a camera where we can like shutter for a very short time at a very specific time, we can image the light at a certain distance to our camera. And then we repeat the same process with a new laser pulse and wait a little bit longer, so give the light more time to move forwards, and so on and so forth. With that we are actually able to make a movie where you can see photography. So the light writing, photo means light, and graphy is the Greek word and stands for writing.
So, after all these technology explanations, I'm going to show you some examples of these movies that we took. Okay, so this is on the left. You see what we call an average picture, which is a picture taken with what could be a traditional camera. And what you're seeing on the right is the same scene, but in which the pulse of light is traveling across it. So what you're seeing more exactly is a scale that we did in the lab. It's a white scale, and it has black lines every foot, so that you see how fast the pulse is moving. And when the pulse of light reaches the background, it reaches the background first in the center. And this is just one example that we were showing at the very beginning, but we also made other films of objects, like daily life objects, and thinking about different themes in photography. And I'm going to show you the next example without the average picture next to it, and I want to let you guess what it is. Yes, well, yes, it wasn't planned. And here I'm going to show it to you again with the average picture next to it, so that you can see how the light is moving across it. You see that the parts that are closer to the camera appear first, because they are the ones that scatter the light first, right? Of course, we were really impressed with the plant and how beautiful it was, the movement of light through the leaves and this abstract animation that happened there. So we decided to kidnap other plants around the lab at Stanford. And this is another one. again with the average picture next to it. And you see that first, so the parts that get illuminated as the pulse moves towards the background get into the darkness. So we like to think that first we see the plant without the shadow, and then we see the shadow without the plant. And all these films and like the technology, we have it in a lab in Stanford, and it was also 130 years ago in Stanford that there was a photographer called Muybridge developing really fast photographic techniques. He was trying to see with a camera something that we cannot see with our own eyes. And he actually tried to test if it's possible that when a horse is running, any of its legs touch the ground, like if there's any moment in time when that happens. And as you may know, he was able to test it, which is in this picture, in this one of the most famous images of Muybridge. And of course, we thought a lot about Muybridge with our ultra-fast technique, and we wanted to pay an homage to this pioneer of fast photography, so we did the following. Of course, as you see in the average picture, we couldn't get the real horse. And we also like to say that whereas Muybridge was using light to capture the motion of a horse, we are using a horse to capture the motion. That's very good. And of course, thinking again about traditional themes in photography, of course, we couldn't miss doing portraits, or what we like the trend right now, it could be more selfie, you know? So that's also something that we did. The first one is Thomas. You're seeing the legs and the hand. So again, the parts that are closer to the camera will appear first. And the ears illuminate for a very long time. We don't know why. The second one is me. And again, you see the legs, and then the hand and the torso. And you see that we use goggles, and that's because the lasers that we use could damage our eyes. So since the beginning we were joking that if we can never present this project anywhere, at least maybe we could appear in some laser safety guides. And the third one is Philip. And I want to point at something that happens in the background. And it's like these very small circles, and that's because there are tiny pieces of dust in some of the optics in the lab. Let me try to point at something. So for example, this. And I will show now the three of them together.
So there are two things that you want to take home. One is that light does move at the finite speed. So it does always take some time for light to move from A to B. That means any image you see is always an image from the past. When you look into the mirror, what you see is an image of your younger self. Maybe a few nanoseconds younger, but still. That's the one thing. The other thing is, we said it moves at the speed of light, and you can see it here move across this ruler at the constant speed, and then when it reaches the screen, all of a sudden it blows up, and it looks like as if it was going much, much faster, right? So that's a small riddle to take home, whether light can move faster than the speed of light. I'm sure you can solve it. If not, then we're happy to answer it, of course. If you liked our movies, please visit our website, seekphotography.com. And we would like to thank Brennan Klopfer, who is a grad student working with us, and also Mark Kasevich, who did not fire me after we had misused his lab for many days. And of course, yeah, thanks that you came today. Thanks for having me.